Hi, this is Matthew Pellin going over all of the work that I've done in OPL this semester. So the first exercise was just to do something interesting with the lambda calculus. So at first I just started with doing all of the examples we did in class, basic arithmetic, numbers, booleans, etc. And then I moved on to recursion, which, since I'm implementing this in Python, which I'm familiar with, which is why I chose it, I discovered that Python doesn't short-circuit booleans in lambda calculus. So normally, makefac in the lambda calculus would look something like this, where you check if x is 0, if it is, return 1, otherwise return x times x minus 1 factorial. That doesn't work in Python because it will always evaluate this expression before passing it to the boolean, which means that there was always infinite recursion, and that took me a while to track down why I was getting all that infinite recursion, and it turns out it's just Python doesn't short circuit because it doesn't have the beta rule. So it took me a while to figure out a workaround for that, but the workaround I ended up finding was just using, instead of just passing it 1 or x times x minus 1 factorial, I basically wrapped those in a lambda that would then return 1 or return y times y minus 1 factorial. So then I pass those lambdas to is 0, which means Python won't evaluate the body of the lambda yet. And then once the boolean returns which one of those to call, then I pass it x. So that was the hardest part of getting recursion to work, was just trying to make that workaround so that Python could work with it. But once I got that done, it was pretty simple to get it all working. And once I had basic recursion working, I was able to use it for other functions. Like I created a recursive division function, which basically created a for loop, so that when you were doing x divided by y, you increment z from 0 until z times y is greater than x, and then you just return z minus 1, which is integer division. And so obviously for that I had to make some comparator functions like greater than, equal to, etc. And once I had those, the interesting thing I wanted to make was a binary search. So obviously to do a binary search, I first had to define an array. So my array structure is like this. It's a pair of size minus 1, or the index of the last element, paired with the actual array, where the actual array is a pair of the elements 0 to n minus 2 subarray, and then the last element. So if your array in Python looks like this, my array would look like this. This section of the array, at least. Notice that there's an extra 0 here. That's because the way my functions are designed, it requires that each element be the second element of a pair. So this first element needs to be the second element of a pair as well for the functions to work. So this 0 exists solely so that it can be the first part of a pair. It's not part of the array, it's not accessible by any of the array functions. It solely exists so that this 0 can be part of a pair. So then in total the array structure would be like this. So you have the index of the last element, and then this recursive pair structure that houses the actual data in the array. So once I designed the array structure, I got to write all the functions for the array. And the only ones I needed were appending. I used that for creating arrays, which appending was actually what I designed this array around, which is why it's structured as it is, because appending is very easy with this, because you just increment this value by 1, and then the second element of the array is the original array substructure paired with the new element. So that's, I was thinking of appending when I created this structure, which is why it's that simple. And then indexing, you just, if you want the second index, for example, you take this value, the index of the last element, and subtract the index of the element you want, which in this case would be 1. And then that many times you call this r-iter function, which passes true to the array, which means that you go from here to this subarray. And then you do that index of last element minus index of element number of times, which gets you to the subsection whose second element is the element you want. So once you're there, you just pass false, which gets you that second element. So that's how indexing works. And then getting a subarray is similar. It does from I to j. Use j similar to how we just did indexing, except you don't pass false at the end, so you stop when you have the subarray. And then to go from I to j, you set this first value to j minus I. So that doesn't actually remove the values before the ith element, but it just tells the array that they don't exist, is how I chose to do it, because it's just the simplest way to make it return a subarray structure that is correctly indexed and appended to. So once I had those, I could write my binary search, which unfortunately doesn't work. As you can see, it's a lot more complicated than just trying to write a factorial, and somewhere in here I have incorrect logic, and I can't find it visually looking at it, and Python's debugger just isn't very good with this many nested functions. It's just unclear and hard to discern where the issue lies. So due to time constraints and having to move on to the other exercises, I wasn't able to get the actual binary search working, which I'm a little upset about. But I did manage to get the array structure fully functional, and it works really well, which I'm really proud of. So that was most of what I learned, was really just trying to create this array structure. Helped me conceptualize how the lambda calculus can be used to create things that aren't really thought of as functions and to create data structures, which I thought was really cool. So then, just for some examples, like I created all these transition functions just for converting between, so it would be easy to output or easy to convert into lambda calculus functions. So as you can see here, I created just a Python array of 0, 1, 2, converted to a lambda calculus array, added 7 and 9 using my append function, printed it out, and it correctly has the 7 and the 9 in it now. And then I tried printing the subarray from 2 to 4, and it correctly gives us 2 through 9. The third element is in fact 7. And then to show off the factorial, I just called the factorial function on the third index, which is the 7, and it correctly gives us 5040, which is 7 factorial. So creating that array structure really helped me understand the lambda calculus a lot more, and understand just what you can do with it and how to create different things with the lambda calculus. So exercise 2, we were to create an ISWIM interpreter. So I started by just creating an expression class because it helped me to conceptualize everything if everything was an expression, and then some of those expressions are values, which are abstractions, constants, and bars. And then each of them has obviously just the base elements that you would think of to be in it. A constant has an integer, a variable has going to be a string in my case, applications have a function and an arg, operations have the op, the vals the expressions, where the vals are ones that have been simplified, expressions have not yet been simplified. And then I had these simplify functions for each of these classes, where for operations it simplifies the next expression. Applications follow the order as defined by the evaluation contexts, where it first checks if its function is a val, if it's not, simplify it, if it checks if its arg is a val, if not, simplify it. If both are vals, then it calls this beta function, which is defined on abstractions, where the beta function calls self.expression.substitute, passing its the abstractions variable and the value that the application passed to it as the second argument. So the substitute functions just recursively do the substitution all the way down to all of the child elements. And the special cases where it's a little different is if you have an abstraction, if the abstractions variable is the same as the variable currently being replaced, it cuts off the substitution recursion there because you need to maintain the scope of that variable. And then if it's a variable and you're substituting it, it checks if it's the same as the variable that's being substituted, and if it is, it returns that new substituted value. Excuse me. And then I had the delta function as part of the simplification of operations. So this one wasn't too difficult because it was basically just transcribing the functions we discussed in class from the evaluation context and using the context to simplify via the beta rule. So this was definitely the easiest of the three to get working, and I tested it, making sure it could maintain scope, testing substitution, and then as my final test case I gave it this, which was just a big expression that had pretty much everything I could think of to test it against. And I tested it against an outside source as well. It correctly gave out 18, so I know that my implementation is correct, and it shows me the steps so I can make sure it's got the right order of operations. So doing this really helped me mostly just to see how inefficient the standard reduction is, because it's easy to see looking at these classes how every time you call simplify, it recurses all the way down to the bottom level to the simplest expressions, and then does one level of simplification and goes all the way back up, which is obviously really slow because you're doing all that traveling for really no reason, which really helped me when going into exercise 3 with a real machine. But this was really cool to see it actually work and doing all of that simplification of the lambda calculus using these classes. So then it helped me with exercise 3, in which I made a CEK machine. So I started by just copying over all of the classes from exercise 2, except without the substitution and simplify functions because you don't need those anymore. And then a few other changes were that abstractions are no longer values because closures exist and are values, and they just have the abstraction and the sigma. And then there's all the k function, the k classes as we discussed, and I also added this op class, which is a new k class that I introduced, which I'll get to in a minute. So for starting out with the initial CEK, it was just these rule 1 through rule 6, which was just transcribing the rules that we discussed in class into Python, which was really simple because I just had to check what my expressions were instances of, what k was an instance of, and then just apply the rule by calling CEK on the right side of the rule based on what we discussed in class. But then there were a few cases I found where it was failing because we didn't discuss the cases of constants and the cases of operations. For example, if you just pass a constant, like if you pass the number 6 to the CEK machine we designed in class, it doesn't know what to do with it. So that took me a while to chase down and figure out why it was failing, because it kept returning none because it doesn't match any of the cases if you just have a constant and k is not an r. So that's why after figuring out exactly which cases it was failing on, I introduced this new case where if the expression is a constant and k is not an r, then you just return the constant. So this is in cases where you just pass a constant to CEK, or if you have a lambda, like lambda x returns 6 and then you pass it 8. So like that's this example right here, where our CEK, as discussed in class, would just return none because it didn't match any of the cases, but by adding that case at the top of mine, it does correctly evaluate as 6. And then I also had to create a rule for operations, and this is what took me the most time to track down bugs. So there are two cases. First, if there are any expressions to solve. If there aren't any expressions to solve in the operation, they're all values, then you just call the delta function, and then call CEK with that new value from evaluating the delta with the same sigma and k. But then the trick was, when you're evaluating an expression, sometimes it has more in it. It could be an application, like right here we have an application inside of an operation. And what I had originally was I was just passing it the same k because I wasn't really sure what I needed to do there, which resulted in, when you got into this closure here, it went to k.k, which just jumped straight out of the operation and into whatever was calling the operation. So that was, even using the debugger was really confusing me because I would see like we're evaluating this and then suddenly we'd be all the way over here evaluating this operation. So that took me a really long time to track down and figure out exactly what was going wrong. But then when I realized it, I just realized I just need to create some wrapper class for the k, so that when we do this k.k, it goes back to the original k for this this operation, so that we would call that CEK, it would call that function, the function would exit and bring us back to here, and we would go back into this operation case. So that was by far the hardest part of creating this CEK, and it really helped me to learn the most too, because like I said, I just kind of blindly copied these rules from what we did in class, just transcribing them directly, and I didn't really understand why we were necessarily doing what we were doing and like passing sometimes k.k, sometimes k.fn. But having to create my own for the operation really helped me understand how we're maintaining the context with the sigmas and the k's to make sure that we don't lose ourselves. So that was really cool. And as you can see, I gave it the same exact expression as exercise 2, and once I've added in those operations and constant rules, it does correctly exit and return 18. So that's all the work that I've done in OPL this semester. Thank you.